Hello, this podcast is going to be for students who are absent on the day we complete the Parallax Lab Experiment 2. Hopefully you can use this podcast to get a virtual data set. So for Experiment 2, the essential question of the lab is, what is the mathematical relationship between the parallax angle and the size of the baseline? So in this lab, we're going to explore how we change the size of our baseline and how that will affect the parallax angle. For Earth, astronomers have a large baseline, Earth's orbit. They take a measurement of a star in June, and then they let Earth revolve around the sun and take another measurement of the same star in December. And this large distance across space is the baseline, or the distance between those two observation points. In our lab, we're going to have to vary our baseline in a different way. So if we look at the lab procedure, it states, place a ring stand with a pole so that it's 1 meter from the poster with the lines on it. Place a manila envelope with the sequence of holes at eye level 3 meters from the chalkboard, or the poster with the lines on it. Look at the ring stand pole against the lines on the poster through the hole with one eye, then through the second hole with the same eye, and record the shift or the parallax that you see in data table 2. Which line was blocked through the first eye, and then as you looked with that same eye through the new hole, which line is blocked now? And then repeat the step using the first and third hole, and finally the first and fourth hole. Essentially, just like we did in the last lab where we're closing one eye and then the other, we're going to have our baseline be the distance between our viewing points. And instead of being the fixed distance between our two eyes, we're going to use the holes in the manila folder to expand and spread out the difference or the distance that we're taking those measurements at. Recording each time in your data table. So for hole 1 and 2, you're going to note which 2 lines were blocked between hole 1 and 2, and then do the same thing for hole 1 and hole 3, and hole 1 and hole 4. As you can see, because each of the holes is a set distance apart, we're increasing our baseline from 15 centimeters to 30 and then to 45. So take a minute, please, hit pause on this and complete the pre-lab. Knowing the procedure, draw your lab setup described in Experiment 2 and then answer the 4 other questions that follow. Once you've completed the pre-lab, hit play again and we'll go through the answers. So hopefully your drawing has 3 key parts. You've drawn the vertical lines or poster on the wall, the ring stand that's in between, and the manila folder with the 4 viewing points or holes that have been punched through it. You as the observer will use your right eye, possibly both times, to look through hole 1 and hole 2, hole 1 and hole 3, and hole 1 and hole 4. The ring stand will represent the nearby star or star that you're trying to measure to. The lines on the poster will continue to represent the distant stars, and the manila folder with holes will represent your baseline or your observation points. If we look back at the first drawing, in Experiment 1, the baseline was the distance between your eyes. In Experiment 2, we're going to increase our baseline by using the folders with the larger distance between viewing points. On Earth, the largest baseline that the astronomer can use is, hopefully you told me, Earth's orbit, observations taken 6 months apart. And finally, let's examine the mathematical relationship that we should see in our data from today's lab. Complete the chart below based on our knowledge of the mathematical relationship. P represents parallax and B represents the baseline. Well, in order to get the algebraic equation, we need to isolate the constant and put both variables on the other side of the equation. So to do that, to get 1 by itself, I'm going to have to divide both sides by p, because if I divide both sides by p, it moves to the other side. And I can see that b divided by p, division, is a direct relationship. As one goes up, the other will have to go up at the same rate. Thus, we have a direct relationship in order to get a constant result on the other side. If you draw a rough sketch of that graph, we should see that our independent variable, baseline, is on the x-axis, dependent variable, parallax, on the y, and a direct relationship should have a line that starts at the bottom and goes up to the right. As the x increases or baseline increases, our parallax should increase correspondingly. Our verbal statement should be to put that relationship into words. As the baseline increases, the parallax shift increases. And finally, visually, we should be able to show as one goes up, the other goes up. All right, Ms. Schneier and I completed the lab, and I filmed her so that we can get our data set. As you watch, please make sure you record the data in your own table so that you can complete the lab afterwards. All right, we're going to get a virtual data set for our Parallax lab. As you can see, we have our background poster taped to the wall. We have our ring stand 1 meter away from it. And then 2 meters behind the ring stand, 3 meters from the wall, we have our viewing station. And that's set up with manila folders where you can see that there are holes punched into place. So we're going to view from the first, second, third, and fourth hole. And Ms. Schneier is going to help absent students collect their data. So she's going to look through each of those holes and report out which line is blocked by the ring stand against the poster.
All right, so when I look at hole 1, number 16 is blocked. And then I'm going to look with my same eye to hole 2, and 13 and a half, 14 is blocked. So I'm going to do the same thing, go back to 1 for my second one. 16 is blocked again. It should be the same. I haven't moved it at all. Hole 3, 11 is blocked. And then if I go back again, 16 is blocked. And then with hole 4, 8 and a half is blocked.
8 and a half. So I'd like you to take a second before we move on to the post lab and really think about what was the independent variable? What did we purposely manipulate in our experiment today? What's the dependent variable? What were we measuring the response of? And what was our controlled variables? What things did we keep constant and unchanged as we performed the experiment? Understanding what was purposely manipulated, responded, and what was controlled is key to creating a good visual model of this experiment. So now that you've collected the data, your task is to complete the analysis and discussion, answering questions about what the relationship was that you saw, and then completing your visual model, making sure that you're very thoughtful about how you're going to represent the changes on that model. What should be true about the base of the triangle in terms of what it represents? And how should the size of the base of the triangle stay constant or change in your drawings? What should be true about the length or side of the triangle? And how should the size of the length of the triangle stay constant or change in your drawings? And then drawing your 2 models, making sure that you label the baseline, distance, and parallax angle, as well as the nearby and distant fixed stars. Drawing a second model that represents the change that you made in your independent variable, and again, labeling all 5 key parts. And finally, summarizing your drawings and how they illustrate the mathematical relationship between the variables tested. Your summary should include 3 components: the mathematical relationship, with variables, written as a verbal statement. Then you'll need to answer the 2 post-lab questions, making sure that you go back to your data table and support your answer with data from experiment 1 or experiment 2. And you'll be turning this in, as this lab is going to be graded as a performance assessment. So please note, in order to get proficient or a C on this performance assessment, the 3 bullets in bold must be done correctly. Your visual model must accurately represent the manipulation of the independent variable. The visual model must accurately portray the response of the dependent variable. And the controlled variables in the lab procedure must remain constant within the visual model. In order to get a B or an A, the next 2 components need to be accurately done within your models. You need to label all 5 major components of the model accurately: baseline, distance, parallax angle, nearby, and distant stars. And you need to include a summary that's a concise verbal statement that identifies the mathematical relationship and describes the trend observed while using the variables. Thanks for watching. I hope this helps. Would love to see you have a great performance assessment.